Look up tonight. Find the band of light cutting across the sky. That's not a cloud. That's not a trick of the atmosphere. That is the Milky Way, our home galaxy. And right now, as you watch this, you are trapped inside it. Not metaphorically, not philosophically, physically, gravitationally, cosmically trapped. The Milky Way is a barred spiral galaxy roughly 100,000 light years across. It contains between 100 and 400 billion stars. It spins at 828,000 kilometers per hour. And you, sitting in your chair, breathing this air, living this life, are orbiting its center at that exact speed. You didn't choose this orbit. You were born into it. Earth formed 4.5 billion years ago from the same collapsing cloud of gas and dust that became the sun, and together we fell into this gravitational dance. We've completed roughly 20 laps around the galactic center since then. 20 times around a track so vast that one lap takes 230 million years. But here's the question that should keep you awake. What if we wanted to leave? Not to Mars, not to Alpha Centauri, not even to the edge of the solar system, where Voyager 1 currently drifts in interstellar space. I mean really leave. Escape the galaxy entirely. Break free of the Milky Way's gravitational pull and venture into the true void between galaxies. The intergalactic wilderness. The cosmic nowhere. How long would that take? The answer will break your brain. But you need to hear it, because the number isn't just big, it's so incomprehensibly, violently, existentially large that it redefines what distance even means. It turns human ambition into a joke. It makes every sci-fi movie you've ever watched look like a lie. Brace yourself. The truth is coming. Let's start with the physics. Because physics doesn't care about your feelings, and it definitely doesn't care about your spaceship designs. To escape any gravitational field, you need to reach escape velocity. On Earth, that's 11.2 kilometers per second. Fast, but achievable. We've been doing it since 1959. The solar system's escape velocity at Earth's distance from the Sun is about 42 kilometers per second. Voyager 1 hit 17 kilometers per second leaving Earth, then got gravitational assists from Jupiter and Saturn, and now travels at roughly 17 kilometers per second relative to the Sun. It's the fastest human-made object ever launched. Voyager 1 left Earth in 1977. It's now over 24 billion kilometers away. It crossed the heliopause, the boundary where the solar wind gives way to interstellar space, in 2012. Humanity's greatest reach, our farthest emissary. And here's the gut punch. Voyager 1 will never escape the Milky Way. Never. Not in a million years. Not in a billion. Not before the sun dies, swells into a red giant, and incinerates Earth. Not before the Andromeda Galaxy crashes into us in 4.5 billion years. Not before the last stars burn out and the universe goes dark. Voyager 1 is traveling at 17 kilometers per second relative to the Sun. But the Sun itself is orbiting the galactic center at 220 kilometers per second. Voyager's puny velocity is like a mosquito trying to outfly a hurricane. It's not even moving in the right direction to counteract our orbital motion. Even if it were pointed perfectly outward from the galactic center, which it isn't, it would need to reach roughly 537 kilometers per second to escape the Milky Way's gravity. 537 kilometers per second. That's 32 times faster than Voyager 1. That's 1,900,000 kilometers per hour. That's fast enough to cross the entire United States in 18 seconds. And that's just the beginning of the problem. You might think, okay, we just need a bigger rocket. More fuel, better engines, nuclear propulsion, ion drives, antimatter. Surely future technology can crack 537 kilometers per second? Here's where the universe gets cruel. The Milky Way's visible matter, all the stars, gas, dust, and planets you can see or detect, accounts for only about 10% of the galaxy's total mass. The other 90% is dark matter, invisible, undetectable except through its gravitational pull. It forms a vast spherical halo surrounding the galaxy, extending up to 1 million light-years from the center. You can't see it. You can't avoid it. You can't push against it. But it pulls on you. It defines the gravitational well you're trying to climb out of. That 537 kilometers per second escape velocity, That's calculated using the total mass, including dark matter. Without dark matter, escape would be easier. But dark matter is real. It's there, and it doesn't care about your engineering dreams. Think of it this way. Imagine trying to climb out of a well, but 90% of the well is invisible. You can't see the walls, can't brace against them, can't map them. But they're pulling you down with 9 times the force of the walls you can see. That's the Milky Way. That's your prison. And the prison is bigger than you think. The visible disk of the Milky Way is about 100,000 light years across, but the dark matter halo extends roughly 1 million light years in every direction. Even if you somehow reached escape velocity from the visible galaxy, you'd still be climbing through dark matter's gravitational grip for hundreds of thousands of years before you truly broke free. But let's be optimistic. Let's say we build the perfect ship. Nuclear pulse propulsion, antimatter engines, some miracle technology that gets us to 600 kilometers per second. Surely then we can escape? Sure, in theory. But now we hit the next wall, time. Let's do the math together. I promise it's worth it. The Milky Way's visible disk is roughly 50,000 light years from center to edge. We're about 26,000 light years from the center, so we need to travel roughly 24,000 light years to reach the edge of the visible disk. But remember, the dark matter halo extends to about 500,000 light years from the center, or roughly 474,000 light years from our position. At 600 kilometers per second, how long does it take to travel 474,000 light years? First, convert light years to kilometers. 1 light year is about 9.46 trillion kilometers. So 474,000 light years is roughly 4.48 quintillion kilometers. Divide by 600 kilometers per second. That's 7.47 quintillion seconds. Convert to years. Divide by 31.5 million seconds per year. The answer? Roughly 237 million years. 237 million years. To put that in perspective, that's longer than the entire existence of dinosaurs. Tyrannosaurus rex lived about 68 million years ago. If we launched our escape ship when T-Rex was alive, it would still be traveling today. It would have witnessed the asteroid impact that killed the dinosaurs, the rise of mammals, the evolution of primates, the entire human species, from first upright walker to you watching this video, would have evolved, built civilizations, and sent this ship all while the ship was still en route, and that's at 600 kilometers per second. 35 times faster than Voyager 1, using technology that doesn't exist, fuel we can't produce, engines we can't build. But wait, it gets worse. Let's talk about fuel, because speed requires energy, and energy requires mass, and mass requires more energy to accelerate, and suddenly you're in the rocket equation's death spiral. The Tsiolkovsky rocket equation is merciless. The amount of fuel you need grows exponentially with the velocity you want to reach. To get to 600 kilometers per second using chemical rockets, you'd need more fuel than exists in the entire solar system. More fuel than all the hydrogen in the sun. It's not an engineering problem. It's a physics wall. Nuclear propulsion? Better. Project Orion, studied in the 1960s, proposed using nuclear bombs detonated behind a spacecraft to push it forward. Theoretically, an Orion ship could reach 3 to 5% of light speed. That's 9,000 to 15,000 kilometers per second. Suddenly, our 237 million year journey drops to a mere 9 to 15 million years. But Project Orion was never built. It would require thousands of nuclear weapons. It would violate international treaties. The ship would weigh millions of tons. And even at 5% light speed, the journey is still longer than the entire Cenozoic era, the age of mammals. Antimatter, the holy grail. Matter-antimatter annihilation converts 100% of mass to energy compared to nuclear fusion's 0.7%. An antimatter rocket could theoretically reach 50% of light speed. Now our journey drops to just under a million years. But we can't produce antimatter in bulk. The total antimatter ever created by humans wouldn't power a light bulb for an hour. Storing it requires magnetic traps at near absolute zero. 1 gram of antimatter costs roughly $62.5 trillion to produce. We'd need tons of it. And even at 50% light speed, even with antimatter, even with perfect technology, the journey to escape the Milky Way would take longer than Homo sapiens has existed as a species. But here's the hook that should truly terrify you. Even if we solved the energy problem, even if we had infinite fuel and perfect engines, we still couldn't do it. Because of relativity. Einstein's theory of special relativity tells us that as you approach light speed, time dilates. For the crew on a ship traveling at 99% of light speed, the journey to the galactic edge would pass in mere thousands of years. They'd age slowly. They'd survive. But time dilation is a trap disguised as a gift, because while the crew experiences thousands of years, Earth experiences hundreds of thousands. The universe outside the ship accelerates. Stars die. Galaxies shift. The cosmic microwave background cools. By the time the crew reaches the edge of the Milky Way, everything they knew is dust. Worse, relativity also increases mass. At 99% light speed, a spacecraft's mass increases sevenfold. The energy required to accelerate it further becomes infinite as you approach light speed. You cannot reach light speed. It's not a speed limit you can break, it's a fundamental property of the universe. The universe says no. And even if you could reach light speed, which you can't, the Milky Way is still 474,000 light-years across in the direction you'd need to travel. At light speed, that's 474,000 years of travel time from Earth's reference frame. 474,000 years, longer than the existence of anatomically modern humans. Longer than the entire Quaternary period. You'd launch when Neanderthals walked the Earth and arrive when whatever evolves after us is digging up our fossils. But wait, there's another problem. One that makes everything we've discussed look optimistic. The expansion of the universe. In 1929, Edwin Hubble discovered that the universe is expanding. Galaxies are moving away from us. The farther away they are, the faster they recede. This isn't galaxies moving through space. It's space itself stretching. In 1998, astronomers discovered something worse. The expansion is accelerating. Dark energy, whatever it is pushing the universe apart faster and faster. Distant galaxies aren't just moving away, they're accelerating away. What does this mean for our escape plan? It means the target is moving. The space between galaxies is growing. The local group, our cluster of galaxies including Andromeda, Triangulum, and about 54 smaller galaxies is gravitationally bound. We won't be torn apart by cosmic expansion, but everything outside the local group is accelerating away from us. The nearest galaxy outside our local group is IC 342, roughly 10 million light-years away. But that distance is increasing by about 220 kilometers per second due to cosmic expansion. Every second, the gap grows. Every year, it widens by 7 billion kilometers. So even if you escaped the Milky Way, somehow, impossibly, you'd still be in the local group. And to reach another galaxy group, the distance isn't just vast, it's actively increasing. The universe is conspiring to keep you isolated. In billions of years, all galaxies outside our local group will have receded beyond our cosmic horizon. We won't be able to see them. We won't be able to reach them. The universe will have partitioned itself into isolated islands, each alone in an expanding void. Our prison isn't just the Milky Way. It's the local group. And even that is temporary. In 100 trillion years, all stars will have died. In a Google years, even black holes will evaporate. The universe will be a cold, dark, empty expanse of photons and fundamental particles. Escaping the Milky Way? That's just the first level of the trap. Let's step back from physics for a moment. Let's talk about you, your body, your lifespan. The longest-lived human on record, Jean Calment, lived 122 years. The longest-lived mammal, the bowhead whale, can reach 200 years. Some tortoises live 250 years. Certain clams have survived 500 years. None of them would survive a trip out of the galaxy. Even at our optimistic 50% light speed with antimatter engines, the journey takes nearly 1,000,000 years. You'd need generational ships. Ships where humans are born, live, and die in transit. Where your great-great-great-grandchildren, hundreds of generations removed from you, would be the ones to finally see the galactic edge. But generational ships have problems we can't solve. Genetic drift. After hundreds of generations in a closed population, genetic diversity collapses. Inbreeding becomes inevitable. Unless you launch with thousands of people and perfect genetic management, your descendants will be sick, mutated, or sterile. Radiation. Interstellar space isn't empty. It's filled with cosmic rays, high-energy particles from supernovae, active galactic nuclei, and distant gamma-ray bursts. Earth's magnetic field and atmosphere protect us. A spacecraft has thin walls. Even with heavy shielding, cumulative radiation exposure would cause cancer, neurological damage, and sterility over thousands of years. Closed ecosystems. You'd need to recycle every atom of air, water, and food, forever. No resupply, no external inputs. Biosphere 2, our most ambitious closed ecosystem experiment, failed in 2 years. And that was on Earth, with access to external help. Social collapse, thousands of years in a metal tube, no sky, no weather, no seasons, no escape. History shows that isolated human populations fracture. They develop cults. They go to war. They forget why they left. The ship becomes a floating graveyard of ideology. And even if you solved all of this, genetics, radiation, ecology, psychology, you'd still arrive at the galactic edge to find nothing. No planets to land on, no stars to warm you, just the void between galaxies. The intergalactic medium is so sparse that you'd travel light years between hydrogen atoms. You'd be alone in a darkness so complete that even the nearest galaxy would be a faint smudge. You escaped the Milky Way. Congratulations. Now die in the dark. Let's return to Voyager 1, our actual fastest object, our real-world data point. Launched in 1977. Speed, 17 kilometers per second. Distance, 24 billion kilometers. Direction, roughly toward the constellation Ophiuchus, which is not radially outward from the galactic center. It's moving at an angle, cutting across our orbit like a stone skipping across a pond. At this speed, Voyager 1 will reach the distance of Proxima Centauri, 4.24 light-years away, in about 74,000 years. Not centuries, millennia. 74,000 years ago, humans were just beginning to migrate out of Africa. Neanderthals still walked Europe. The last ice age hadn't peaked, but Proxima Centauri is still inside the Milky Way. It's one star among hundreds of billions. To reach the edge of the visible galaxy, Voyager 1 would need roughly 1.7 billion years. 1.7 billion years. That's longer than multicellular life has existed on Earth, longer than the Great Oxygenation Event, longer than the entire history of complex organisms. Voyager 1 would still be traveling when the Sun becomes a red giant and swallows Mercury, Venus, and possibly Earth. It would still be traveling when the Andromeda Milky Way collision begins. It would still be traveling when the universe is twice as old as it is now. And remember, Voyager 1 doesn't have enough velocity to escape the galaxy anyway. Even given infinite time, it would remain gravitationally bound, orbiting the galactic center in a long, slow ellipse, trapped forever in the Milky Way's embrace. Our best shot. Our farthest reach. And it's not even trying to leave. It couldn't if it wanted to. This is where I need to talk about science fiction. Because fiction has lied to you, not maliciously, not intentionally, but the lies are dangerous because they make the impossible seem inevitable. Star Trek's Enterprise cruises at warp factor 5, covering light years in hours. Star Wars' Millennium Falcon makes the Kessel Run in less than 12 parsecs. Mass Effect's Normandy uses mass effect fields to cheat relativity. These ships cross galaxies in days, weeks, months. None of this is possible, not with current physics, not with any physics we can imagine. Warp drives require exotic matter with negative energy density, a substance that may not exist. Wormholes require conditions that collapse instantaneously. Hyperdrives, jump gates, slip space, all fictional, all beautiful, all lies. Even the most realistic sci-fi fails us. The expanse uses Epstein drives that achieve constant acceleration at 1 g for months, reaching velocities that would require fusion efficiencies far beyond theoretical limits. Andy Weir's Project Hail. Mary uses alien technology to solve problems humans can't. These stories are wonderful. They're inspiring. They make us dream. But they also normalize the impossible. They make us believe that if we just try hard enough, if we just engineer smart enough, we can go anywhere, do anything, escape any prison. The Milky Way says otherwise. The universe doesn't care about our dreams. It doesn't care about our ambition. It set the rules 13.8 billion years ago. And those rules say you are small, you are slow, and you are trapped. Not because the universe is cruel, because the universe is indifferent, but let's go deeper. Let's ask the question underneath the question. Why do we want to escape? Is it curiosity, the human drive to explore, to see what's over the horizon, to map the unknown? That's real. That's ancient. That's why we left Africa, crossed oceans, climbed mountains, and launched rockets. Or is it fear? Fear of being trapped, fear of limits, fear that our story is small, our stage is tiny, our existence is insignificant against the scale of the cosmos. The Milky Way is 100,000 light-years across. We live on a speck of dust orbiting a mediocre star in a mediocre arm of a mediocre galaxy. We want to believe we're bigger than that. We want to believe we can transcend our origins. But what if the desire to escape is the wrong desire? What if the Milky Way isn't a prison, but a home? What if the intergalactic void isn't freedom, but death? Consider, the Milky Way contains hundreds of billions of stars, billions of planets, trillions of moons, asteroids, comets. It contains everything we need to survive for billions of years. Energy from stars, matter for construction, chemistry for life, gravity for structure, radiation shields from magnetic fields, raw materials from supernovae, water from comets, organic molecules from interstellar dust. Outside the galaxy? Nothing. The intergalactic medium is a near-perfect vacuum. Temperature, 2.7 Kelvin, just above absolute zero. Density, 1 atom per cubic meter. No stars to warm you, no planets to land on, no magnetic fields to shield you, no resources to mine, just cold, dark, empty space stretching for millions of light years in every direction. Escaping the Milky Way isn't escaping to freedom. It's escaping into a desert so vast that even deserts seem generous by comparison. It's leaving a garden to die in a parking lot. Maybe the real question isn't how long would it take to escape? Maybe the real question is, why would we ever want to? So if escape is impossible, what do? We build. We explore. We make the Milky Way our own. The galaxy contains roughly 100 billion stars. Even if only 0.1% have habitable planets, that's 100 million worlds. 100 million places we could live, build, grow. We haven't explored 1% of 1% of them. We've barely explored our own solar system. We've sent exactly 12 humans to the moon. We've sent 0 to Mars. We've mapped more of Mars's surface than Earth's ocean floor. The Milky Way is not a prison. It's a mansion with 100 billion rooms, and we've only peeked into the entryway. Dyson spheres, Matryoshka brains, stellar engines. These are theoretical megastructures that could harness the energy of entire stars, reshape solar systems, and support trillions of lives. We don't know how to build them yet. But unlike escaping the galaxy, they're not forbidden by physics. They're just engineering challenges, hard ones, but solvable ones, given time and resources. In 1,000,000 years, if we survive, we could reshape the Orion Arm. In 10 million years, we could colonize the entire galaxy, not by traveling faster than light, but by traveling slowly, generationally, star by star. The Milky Way is only 100,000 light-years across. At 10% light speed, you could cross it in 1,000,000 years. That's long, but it's not impossible. It's not forbidden. It's just slow. And once we've filled the galaxy, once we've built around every star, mined every asteroid, harnessed every joule of energy, then what? Then we look outward, not because we need to escape, but because we're ready. Because we've mastered our home and seek new challenges. Because curiosity is eternal, even if velocity is not. But that future is not guaranteed. It requires survival. It requires wisdom. It requires not destroying ourselves before we get there. Let's end where we began. Look up at the Milky Way. That band of light. That river of stars. Every photon hitting your retina has traveled for thousands of years. Some for millions. You're seeing the past. Ancient light from distant suns. And among those stars, there are civilizations. If they exist, looking back at us, wondering the same things, trapped in their own galaxies, their own gravitational wells, their own cosmic loneliness. The universe is 93 billion light years across. It contains 2 trillion galaxies, each with hundreds of billions of stars. Each star a potential sun for worlds we'll never touch. Life will never meet, stories we'll never hear. And we are here, on this speck, in this arm, in this galaxy, orbiting this star, living this life. We cannot escape the Milky Way, not in any meaningful time frame, not with any technology we can imagine. The physics is clear, the math is brutal, the energy requirements are impossible, the timescales are beyond biology, beyond civilization, beyond comprehension. But here's the final truth that should stay with you. We don't need to escape to matter. The Milky Way is our home, not a prison, a home with 100 billion rooms we haven't visited. A home with mysteries we haven't solved, a home with beauty we haven't seen, a home with potential we haven't unlocked. Voyager 1 will never leave. But it doesn't need to. It's already taught us more than we knew. It's already carried our message into the dark. It's already proven that we can reach, that we can build, that we can dream beyond our atmosphere, beyond our solar system, beyond our star. The terrifying truth about escaping the Milky Way is not that it would take 237 million years, or a billion, or forever. The terrifying truth is that we've been asking the wrong question. The question isn't how long to escape. The question is, what do we build while we're here? Because we're not going anywhere. Not quickly. Not easily. Not ever in any timescale that matters to a human life. But we are here. Now. In the most beautiful, complex, mysterious galaxy we know of, surrounded by stars we can reach, worlds we can explore, and futures we can create. The Milky Way isn't our cage. It's our canvas. And we have 100 billion years of starlight left to paint with. So look up, see the prison that isn't a prison, see the home that waits to be explored, see the galaxy that doesn't care if we stay or go, but offers us everything if we choose to stay and build. The terrifying truth about escaping the Milky Way? We already escaped. We escaped the surface of our planet. We escaped the gravity of our star. We escaped the blindness of our ancestors who looked up and saw only lights, not worlds. The next escape isn't out. It's up. It's deeper. It's into the galaxy we already have. Brace yourself. The journey doesn't end at the edge of the Milky Way. It starts right here.